This is part 3 of section 3.5, Proofs in Set Theory. In this video we're going to look at Venn diagrams. The relationships among sets can be represented visually using Venn diagrams. Each set is represented by a circle or some other closed geometric shape enclosed in a rectangle which represents the universal set U. A Venn diagram for two sets A and B is shown in the figure. And here's a Venn diagram for three sets A, B, and C. Note that we want to include all possible intersections of the three sets. In these diagrams, the elements of the universal set correspond to the points inside the rectangle, and the elements of each set correspond to the points inside each circle. We can draw the circles corresponding to the sets to illustrate the relationship among sets. For instance, to illustrate two sets A and B, where A is a subset of B, we can draw the Venn diagram as follows. We can shade particular regions to illustrate various set operations. The shaded region in the Venn diagram below corresponds to the union, A union B. The shaded region in this diagram corresponds to the difference, B minus A. There are many relationships among sets involving unions, intersections, differences, and complements. We can sometimes use Venn diagrams to discover relationships among sets or to test conjectures. Note, however, that a Venn diagram by itself does not constitute a proof that a conjecture is true or that a conjecture is false. In order to establish such a relationship, we need to write a formal proof using the definitions of set, inclusion, and equality. Here's an example. Suppose we want to determine whether or not the following statement is true. For all sets A, B, and C, A union the quantity B intersects C is the quantity A union B intersects C. We can start by using Venn diagrams to illustrate the two sets. So the set A union the quantity B intersects C is illustrated by this Venn diagram. The set quantity A union B intersects C is illustrated by this Venn diagram. Now, comparing the two Venn diagrams, it certainly seems that the two sets are not going to be equal in general, and hence that the statement is false. Just stating this, based upon the Venn diagrams, however, is not sufficient for a proof. To prove the statement is false, we need to find a specific counterexample, namely sets A, B, and C, such that A union B intersects C quantity is not equal to the quantity A union B intersects C. The Venn diagrams can be helpful in finding such a counterexample. From the diagram, you can see that we should choose sets A, B, and C so that there are elements in A which do not belong to C. So for instance, we can choose A to be the set containing 1, 2, 3, B the set containing 2, 3, 4, and C the set containing 4, 5, and 6. Then if we compute A union the quantity B intersects C will be the set A containing 1, 2, and 3, union the intersection. The intersection turns out to be the set containing just the single element 4, so taking the union we obtain the set containing 1, 2, 3, and 4. The set quantity A union B intersects C, however, when we first take the union, we obtain the set 1, 2, 3, and 4, and then when we intersect this with the set containing 4, 5, and 6, we obtain the set containing the single element 4. So obviously the two sets are not equal, and thus the statement is false. Now when you're looking for a counterexample, you can always basically choose some sets at random. See if they work, see if they serve as a counterexample. If they don't, you might be able to figure out how you need to modify the sets in order to obtain a counterexample.